An inverse function is a function that undoes the original function. So whatever you put into the original function and get out, your inverse would undo that and get you back to your original. For an inverse function to exist, it needs to be a one-to-one function, meaning it needs to pass the vertical line test and the horizontal line test, meaning a vertical or horizontal line can only cross your graph once. If your original function is noted as f of x, then your inverse function would be f with a low negative 1 of x. That notation means the inverse. Or if your function was g, then it'd be g with a low negative 1 exponent of x. To verify that you found the original inverse, you want to use a composition of functions. You want to take your inverse, plug it into your function to see if it simplifies down to x. Or take your original function, plug it into your inverse to see if it simplifies down to x. We want to go ahead and find our inverses here. Our original function says, well, I'm taking my input and adding 7. So I'm assuming most of you would say to undo that, I just have to take my input and subtract 7. So that would be your inverse. Now, to verify that, we're going to take our inverse here and plug it into the original. So we're going to take this right here and plug it in right here for x. When we do that, we get this. Don't need the parentheses. We simplify, we get x. Since it simplifies down to x, we know we have the correct inverse. The next one says, well, whatever my input is, I'm going to multiply it by 5. So therefore, to find my inverse is going to undo that, so it's going to take whatever I put in and then multiply it by 1/5 or divide by 5, whichever one you prefer. Once again, to find the inverse, you need to go ahead and take this, or not to find it, but to verify it, you need to take this right here, plug it in to your original function for x to see if it actually does simplify down to x. When we do that, it does simplify down to x. It's pretty easy to find your inverse functions when you're only dealing with one operation and you're just trying to undo that one operation. Here we have two operations going on. We're multiplying by 3. We're going ahead and adding 2. When you have more than one operation going on, you may want to follow these steps. To find your inverse, you want to switch your x and your y. Then solve the new equation for y. So when we look at our original problem, we have an h of x. That's just like your y. So we're going to start off with your original problem. We're then going to go ahead and do the first step that says switch x and y. We now want to take this green equation, go ahead and get y by itself. So we'll go ahead and subtract 2. Then we'll go ahead and get rid of the timesing by 3 and divide by 3. This is your inverse. Since we started out with an h of x, we should write this as an h low negative 1 of x equals our problem. Now, we need to go ahead and verify that. So we're going to go ahead and take this, what we got for our inverse, and plug it into your original. When we plug it into your original up here, for your x, it should simplify down to just be your normal x. That's what this notation is saying. Take your inverse, plug it in for x. So we're taking your original function, plugging in your inverse. You'll notice the 3's drop, then the 2's drop. Since it simplifies down to x, we know we have the correct inverse. We want to go ahead and find our inverse of our function. But first, we're going to find our range and our domain. Your domain is fairly easy. Your domain is just given to you right here. Your inverse, though, is what you're getting out of this. Well, when you're looking at this, remember your x squared takes anything and squares it, so it's going to be positive or 0. But then you're going to take anything that's positive or 0, and then you're going to subtract 3. So that means your range would have to be greater than or equal to -3. Now, what we talked about in the last problem for finding inverses was to go ahead and switch your x and your y, and then go ahead and solve the new equation for y. So we'd have to add 3. We'd then have to go ahead and take your square root. Your inverse, though, is only the positive root. Why it's a positive root we'll talk about in a little bit here. For right now, let's go ahead and graph our original function up here. All we're doing is making a t-chart. We know we can only choose values greater than or equal to x. So that's why I've only chosen positive values for x. Plug in your 0, and you do your subtraction of 3. Plug in your 1, square it, subtract 3. Plug in your 2, square it, subtract 1. Plug in your 3, square it, subtract 6. Plug in your 4, square it, subtract 3, and you get your 13. So plot those points and draw in a smooth graph connecting those. You get a graph that looks like this up here in red. The red graph is a 1-to-1 graph because a horizontal line would cross your red graph only once. A vertical line would only cross your graph once. When you're trying to find your inverse, you got to think, okay, what will undo my function? Well, to undo it, let's take a look at the graph of your inverse. Your original says if you plug in 0, you get out -3. So your inverse has to undo that. So here you have a 1, you get out -2, your inverse has to undo that, and so on. And you notice your t-chart, your xy chart, is basically just flipped. So let's go ahead then and graph those points on our graph. Then draw in a smooth curve to connect all those. We then have the graph of your inverse up there in purple. You'll notice your purple graph only goes from the x-axis up. So that means the range of the purple graph is greater than or equal to 0. You'll notice on your graph it only starts at -3 and goes to the right. So that means your domain is greater than or equal to -3. If we had used the plus or minus here, it would also give you the reflection of the purple graph over the x-axis underneath, which means it would not be a function, it would not be 1-to-1. So what do we notice here? When you look at the table, you switch your x and y's. What do you notice about the domain and the range of your function and your inverse? Your domain and range are switched. When you look at your graph, how do you go from your original function to your inverse? It's really the reflection over the y equals x line. And that's the dotted line that we have drawn in here. You reflect the red over that line and you get the purple. You reflect the purple over that line, you get the red.